Welcome back. Today is lecture 24. We are going to conclude our discussion on L-gas gas Hemts, just the normal baseline Hemts. Okay, and in the next week we are going to talk about sideromorphic Hemts, indium phosphide Hemts, and metamorphic Hemts for a total of 4 lectures starting lecture 25 next week. So today in lecture 24 we are going to conclude L-gas gas Hemt by discussing the small signal model, and then we will discuss some noise also, and also we will talk about how to estimate the delays in such a Hemt, how to extract the velocity in such a Hemt. If you have a material, for instance gallium arsenide channel, how do you extract the carrier velocity in such a Hemt. Okay. So over to the whiteboard here. What I am showing you here is basically a small signal model, a small signal diagram of such a Hemt. Again the same discussion on distributed versus lumped hold true as we discussed in our MESFET, but more importantly the small signal model of a Hemt is almost identical to that of gallium arsenide MESFET. There is no difference here. The expressions for cutoff frequencies are also identical. There is no difference here, so we should not spend much time here, but I will try to again emphasize that this is your intrinsic device, which is all that actually matters most importantly for understanding. This is your gate drain capacitance. Between the gate, this is your gate, this is your drain, correct. So between the gate drain there is gate drain capacitance, this is gate source capacitance. Okay, this is your current GM VGS, that is your essentially IDS, the current. This is your drain to source capacitance, you can ignore that, but in terms of in depletion this actually can become prominent. And of course you have Rin. Rin is your channel, sorry not the channel, the barrier resistance. So the gate leakage Rin here. So the barrier, the L-gas barrier is an insulating barrier, so that is the resistance. It should ideally be infinity, but it is not infinity, so you have it there. Okay. Outside are all extrinsic, so this is your drain excess resistance plus drain contact, gate excess, this is the gate resistance, the gate metal resistance. This is your source excess resistance plus the source contact. This is your pad capacitance on the drain, this is your pad capacitance on the gate. Source inductance LS is very important, gate inductance and drain inductances. Okay. So this is your small signal model for your L-gas gas Hemt, and you can see that this is the almost the same actually as that of a small signal model of MESFET. Okay, except that in MESFET your depletion keeps happening, with gate bias you keep depleting the channel. In Hemt you do not do that. You deplete the channel, but your channel, your metal, your gate metal to your channel, this is your channel 2DG channel, this distance remains constant, which is the L-gas thickness below the gate. So in Hemt capacitance is constant, so this essentially manifests as a gate channel capacitance in some way. So you can say that the gate to channel distance is constant, although the channel is depleted, the 2D electron gas is depleted with higher negative gate bias, but the capacitance does not change between the gate and the channel, okay, to a first order. However, in MESFET you have no 2DG channel, you have a dope layer, and you keep extending the depletion until the channel pinches off. So your capacitance in case of a MESFET is highly dependent on the gate bias, okay, and that is why people, to avoid that, people use a graded layer and delta dope layer and so on and so forth. Okay, but this is the small signal model. This is your cutoff frequency expression, which is identical to that of a gallium arsenide MESFET. In fact, for any Hemt, any FET you can use the same concept. GM FT directly goes as GM, the transconductance has to be really high, and you can see that this is your gate source capacitance, this is your gate drain capacitance, source resistance, drain resistance, this is your output conductance. Output conductance we already discussed what it is. This is again gate drain capacitance, GM, same thing. Okay. So essentially you have to minimize RS, RD, you have to also minimize CGS, CGD for higher FT, and you have to maximize RDS, or your output conductance should be 0, your output resistance should be almost infinity, that is ideal. That is all fine. But FT actually depends on this expression is actually 1 by tau total. This tau total is actually the delay, the total delay of the electron as it goes from the source to the drain. So as an electron goes from source to the drain, it encounters many charging discharging capacitors, it encounters the below the gate transit time and so on and so forth. So the total delay actually gives you the cutoff frequency here. And what is the total delay? You can broadly define the delay into 2 parts. One is the gate delay actually, okay. So one is your gate delay, I will come to that. The delay that happens below, not below, essentially the delay that happens due to the gate, there is a gate delay. Gate delay has 2 parts actually. One is your transit delay, which is essentially the electron takes finite time to travel below the gate, this intrinsic gate. It takes a finite time to travel below the gate, and that is basically your gate length divided by the saturation velocity. Highly scaled devices, we are talking about highly scaled devices. So, this is your transit delay, the electron takes that much time to travel below the gate. The gate also has a fringing coupling capacitances with this gate drain excess region and the gate source excess region. We call that extrinsic delays. This is your intrinsic delay, this is your extrinsic delay. The extrinsic and intrinsic delay are both, some literature they club them under gate delay, some do not, but some literature do, we are following that. So, gate delay consists of intrinsic delay, that the electron takes time to travel below the gate, okay, and extrinsic delay is basically the charging of and the discharging of the capacitances between the gate and the excess region charges. There is a gate drain excess region, there is a gate source excess region. So, the gate will fringe, of course there is a fringing capacitance, it will couple with capacitively with the electrons, the 2d electron gas in the excess regions. So, this is called the extrinsic delay, and this too consists of the gate delay, and then of course then there is a parasitic delay. Parasitic delay comes because of the contact resistance mostly, okay, and other maybe it will have package and other things, but in general the parasitic resistances keep coming in the picture here, okay. So, the idea is how do you extract different fractions of delay, how do you extract extrinsic delay, intrinsic delay, parasitic delay, which fraction of the delay matters more. As you will see that if you scale down the gate length from 100 nanometer, 60, 40, 20 nanometer, ridiculously scaled gate lengths, the intrinsic delay does not matter as much, the dominant delay is the parasitic delays, extrinsic delays, etc. Okay. So, to do that, what people have, there are many ways, of course quite a few ways, but what ways that are most commonly reported or popular, we will adopt that for 3.5 Hemts or FETs, which is that you first try to find out the combination of the intrinsic plus extrinsic delay, and once you find it out you can extract the parasitic delay. So, what people do is that, okay, this slide might look a little busy, but we can go step by step. As I said, gate delay is intrinsic plus extrinsic delay, then there is parasitic delay. Now, what is intrinsic delay? Intrinsic delay is basically the time taken by the gate to travel below the gate, which I said Lg is divided by V set, which is also expressible as this quantity, which means the intrinsic gate source capacitance, the intrinsic gate drain capacitance, you add them together because they are in parallel, and then divided by the intrinsic GM or the transconductance of the device. This gives you the intrinsic delay. This is also equal to Lg by V set. Okay, please remember that. The extrinsic delay is of course the same, but you are talking about extrinsic capacitances divided by GM. Okay, and the parasitic resistances will actually come the contact resistance here. The excess resistances also will matter here. Okay, and so you have the two excess resistances, they will include the contact resistance plus this expression where you have G0 by GMI, which is the output conductance divided by the intrinsic transconductance into the summation of the source and the drain capacitances plus again the CGD. Okay. So, this mathematics is all fine, but what is it that you practically can do to extract out these different delays. So, you can see there are two plots here for, actually there are two different gate lengths. You can see this is a 200 nanometer gate length Hemt, this is a 40 nanometer gate length Hemt. This actually your data was for gallium nitride Hemt, but it does not matter, the concepts are identical for gallium arsenide Hemts also. This is a 200 nanometer gate length, this is a 40 nanometer gate length, but we can just choose one of them. So, what is plotted on the y axis and what is plotted on the x axis? If you see carefully, if you choose the gate, say 200 nanometer gate I have for a particular device, this is particular device, you can, what is x axis? X axis is 1 by the drain current, very interesting. So, essentially you bias the device at different gate voltage. Suppose your pinch off voltage is minus 3 volt, at minus 3 volt your device becomes off. So, you measure the FT of the device at say minus 2.5 volt, minus 2 volt, minus 1.5 volt, minus 1 volt, minus 0.5 volt, etc. You can have even more finer spacing, minus 2.4, minus 2.4, minus 2.3, minus 2.2, etc., etc., minus 1.2, minus 1.1, etc., etc. You can have 10 different points. Okay, you measure the FT, and there is a way to measure FT. We will talk about that towards the end of this course. You can measure FT experimentally. So, you find out the FT cutoff frequency, and once you find out the FT, you can do 1 by 2 pi ft and you will get the delay. So that delay is this data points, this you see there are some 10-20 points here, no, those are the points that are plotted with respect to ID, 1 by ID. So at different gate biases, if you have a gate bias of say minus 2.5 volt, minus 2.4 volt, minus 2.2 volt, 3 volt, etc., these are gate bias. You get these different points, correct? You get these different points. For each of these gate biases, your drain current also will change at a constant. If you keep the drain voltage constant, your drain current ID strongly depends on the gate voltage, of course. So as you keep increasing the gate voltage, your drain current also will increase in the positive direction, I mean. So you know the drain current, you know, for this maybe some milliamps, for this okay some other milliamps, etc. So you do reciprocal of that 1 by ID. So what happens is that you are increasing the drain current in this direction. So your delay will keep decreasing. Why? While the delay keep decreasing, the delay will keep decreasing with higher drain current, because you are charging the capacitor or discharging the capacitor faster. With higher current, your capacitance charging and discharging will be faster. Rule number 1. So with higher or faster capacitance charging discharging, your total delay will come down. Eventually it will start going up, because at this point you are approaching the pinch off voltage of the device. Once you are approaching the pinch off voltage of the device, you are actually you are increasing the drain current in this direction. So you increase the drain current so much that your gate drain diode will turn on, or heating effect will come in, your current will saturate. When I say saturate, I mean to say with respect to the gate, okay, your GM will start falling beyond this point. Beyond this point your GM will start falling, you remember. So you have a GM versus VG. So if you are minus 3 volt here, then the GM will start like that and the GM will fall. GM is the derivative of the drain current. So once the GM starts falling, your this part, your current starts or your delay starts increasing, because your FT starts falling. Your GM is directly related to FT. So if your GM falls down, your FT also will fall down. If your FT falls down, it is equal to 1 by 2 pi t, no, delay. So the delay will shoot up. So this delay shooting up is because the GM is falling and you are getting to higher current levels. You know, the current is basically saturating, you know, you can say, with respect to the gate bias. So the GM start falling, and the derivative of a straight line is, you know, it's 0. Essentially the GM will start dropping sharp. That is why your delay shoots up. So what you do at this point is that is why you do not consider that point, you only consider the minimum point here, this minimum point, you ignore this part, okay. And you have this slope coming here. As I told you, this current is increasing in this direction, so your charging delays are decreasing. You come to this point, extrapolate up to 0. What is 0? 0 is 1 by ID is 0. 1 by ID is 0 means ID is infinity, which is not physically or practically possible, but theoretically at a drain current of infinity, your charging delay will be 0. If you have infinitely high drain current, you will have infinitely small charging delay or 0 delay. So this point is 1.4 picosecond in this case, is your extrinsic plus intrinsic delay. This excludes the parasitic delay, because the parasitic capacitors can be charged by the drain current infinitely fast, and that is why your parasitic component, this component will become 0 once your drain current becomes infinity, because the drain current will charge it infinitely faster, okay. So this point is constant, by the way. At any drain current, you have a total delay of intrinsic plus extrinsic delay here, okay. This is your at 0 point, and at this minimum point, no, from that minimum point to this point, you can see this is 160 femtosecond or 0.16 picosecond, that is your parasitic delay. So this delay essentially this delay is a combination of parasitic delay plus extrinsic plus intrinsic delay, but this is the minimum extrinsic plus intrinsic delay you can get. So all of these are parasitic delay. So at the minimum point, this is your true parasitic delay corresponding to the highest max GM. So you always get the highest FT whenever for a device, you get the highest FT or highest cutoff frequency for a gate bias that gives you the highest GM, more or less. So this point, this minimum point corresponds to that point actually, okay. So this point corresponds to the peak FT or peak GM, you can say peak GM, more or less, very close to that, okay. So this point is your peak GM point, this point is your peak GM point. So you subtract that from the baseline intrinsic plus extrinsic, you get the parasitic delay. So now you know the parasitic delay. In this case this is 0.16 picosecond, in this case this is 0.29 picosecond. So that is your parasitic delay, but you still do not know how much is the intrinsic delay, how much is the extrinsic delay. So for that what they do is that you do this exercise, whatever you have done here, you do for 10 different devices, maybe 5 different devices of different gate length, 40 nanometer gate length, 60 nanometer, 80 nanometer, 100 nanometer, 150 nanometer gate length. You know, you keep changing the LG, and for each of them you do 10 points to extract this. So you have to do like lot of measurements, each measurement takes time. So this is a laboriously time taking process, and you have to do it very carefully. For each point you have to extract the cutoff frequency, which is also not trivial. You have to de-embed the parasitics, look at S parameters, many things are there. Okay, we will go to the S parameters towards the end of this course, but once you do that for different gate length you are able to do this. So for this is 0.16 picosecond for 200 nanometer gate length, this is 0.29 picosecond for 40 nanometer gate length. So you plot with respect to gate length, you can plot the different extrinsic plus intrinsic delay. You are plotting this quantity or this quantity. Okay, you are plotting that quantity there. So you are able to get different data points, and they will all lie in a straight line. Okay, they will all straight line like this. Okay, the slope of this line is your velocity, because this is your delay and this is your gate length. Okay, so you get a slope of the line will be velocity. However, this point here will give you the extrinsic delay. This is 0.1 picosecond here. The slope will give you the velocity of the carrier, because as you are changing the gate length, what happens is that your intrinsic delay changes. Why? Because intrinsic delay is nothing but LG by V set. Now V set remains constant. So if you are changing the LG, your intrinsic delay changes. So with higher LG you have higher delay. That is why you have with increasing LG you have a higher total delay. However, extrinsic delay, the extrinsic delay does not depend on the gate length, because extrinsic delay is nothing but how is the gate coupling to the electron gas here, you know, on the other side of the gate. So that does not depend on the gate length LG. That is why that component is fixed. This is your component, fixed component. On top of that you are adding the intrinsic delay, which is increasing with gate. That is why you have a gate length dependent intrinsic delay and a gate length independent extrinsic delay, and from the slope of this you can find out the velocity, and from this intercept you can find out the extrinsic delay. So this is the way you find out the delays, extrinsic delay, intrinsic delay, and parasitic delay, as well as the velocity of electrons in the channel from FT measurements. You know, it's a very laboriously long process. However, the last topic that we are going to discuss in LGAS gas Hemts, in a baseline as LGAS gas Hemts, is the noise model or the noise performance. So here what I am showing you here is actually the noise small signal model of an LGAS gas Hemts. It looks almost identical to that of a MESFET, if you recall. Okay, and here you can see that again this is your gate drain capacitance. Maybe I will use a different color here. This is your gate drain capacitance. Okay, this is not a good color. This is your gate to source capacitance. This is your output channel, this is the output resistance, this is your barrier resistance, it should be infinity, I told you, right, the LGAS barrier. Okay, however in a noise model we do not have to consider many of the things as in a normal small signal. What is more important here is this, which is actually your drain noise. This is the dominant source of noise, and this is your drain noise, and the source of this noise is the carrier itself flowing in the channel. The fact that there are electrons flowing in the drain channel, the carriers themselves are the reason of this noise, which means you have a higher drain current, you will have higher noise power actually. Okay, so this is a very important noise. Another noise is this ING, which is your kind of a gate induced noise, but this can be ignored if you are to a large extent. For instance, okay, the gate induced noise becomes very prominent in a MESFET, by the way. This is the gate resistance noise, the thermal noise that comes from the gate resistance. This is your noise that comes from the thermal resistance of the source. The drain does not matter there, we have the drain current noise already there. So the gate and the source resistances contribute to thermal noise. This is the induced gate noise I already told you about. So now we are not going through the derivation, but Pn is the noise power density. Okay, the noise power, you can say this noise power density, this expression that I am showing you here is particularly for the drain current, the drain noise, this that is happening here. No? So, the drain current contributing to noise is expressed as a noise power density. So, here you can see that of course, the higher noise power density means you have more noise. So, you have a drain current. So, which means if you reduce the drain current, your noise power will go down, which is good, very interesting. D is the diffusion coefficient in a way of the carrier, it depends on temperature. Vs is the velocity of saturation, Lg is the gate length, delta F is the bandwidth over which you are considering this. Okay. So, this is very interesting. This means that your noise power will reduce if you are operating the device at lower drain current. If you are operating the device at lower drain current, which is very different from a power Hemt. In a power Hemt you want the current to be very high so that you can get higher power output, but in a low noise amplifier you want actually to bias the device so as to get a lower drain current, which will enable you to get a better noise power, a lower noise power. Okay. So, the carrier velocity Vs, you can see that Vs is actually in the denominator. So, if you have a faster Vs, you have a lower noise power, which is good. So, you need to have higher velocity of carriers, electron velocity, and so the channel such as indium gallium arsenide channel, which can offer an inherently better velocity of electron than say gallium arsenide, will give you lower noise because the velocity goes as cube and velocity of in gas is higher than gas. So, choosing or selecting the channel material is also very important, by the way, apart from other things. So, velocity has an important role to play, and Lg, the gate length, is exponential to the gate length. If you have a lower gate length, your noise power will reduce exponentially, you see, okay, and it goes as cube of the velocity. So, these are two khatarnak, two very important parameters. The gate length has to be as low as possible and the velocity should be as high as possible. In that case, your noise power will be as low as possible, and that is what you want. So, a more pictorial or a qualitative assessment is that imagine there is a motorbiker who is going at very high speed. There are two people standing here, the opening on the door is very wide here on the wall and the opening here is very narrow. So, this corresponds to a larger gate length, this corresponds to a smaller gate length, this corresponds to larger gate length. So, this person will hear more noise, he has to put hands on the ear, but this person will not hear as much noise because the opening is very narrow, correct. So, the gate length should be as low as possible for a lower noise. Similarly, if you consider that you have a identical opening, say this opening. If the motorcyclist is going at a lower speed, then this person has to hold the ears because the noise is too much. But if the motorcyclist goes in a very fast speed, you couldn't even know when it passed away, then he may not have to hold his ears because the motorcycle will be boom, very fast he went away, the noise is low. That is why the velocity has to be very high and the gate length has to be very low. These are two important aspects, and of course mobility has to be also high because mobility helps bring down the parasitics. And if you reduce the parasitics, you get a higher gain, and that is very important because parasitic, especially source excess resistance, can actually kill your gain, your GM, and that is not a good thing. So, what I am showing you here is now an FG chart. F stands for noise figure that we already talked about. Noise figure or NF is basically the 10 log of the signal to noise ratio at the input divided by signal to noise ratio at the output. The signal to noise ratio at the output always degrades compared to signal to noise ratio at the input, because not only the gain and signal are both getting amplified, but the device itself is also adding its own noise. So, the signal to noise ratio at the output is always lower than that of the input. So, this ratio is always more than 1. The best case would be 1, in which case the noise figure will be 0 dB, which is the ideal, but you want to bring it as close as possible to 0 dB as possible, okay. But still 1, 2, 3 dB etc. are also very common in many low noise amplifiers. You should keep it as low as possible, by the way. So, F stands for that noise figure and G stands for gain. So, noise figure and gain are very important in a low noise application. So, here what they are showing here is, by the way, this Pn. This Pn is not the same Pn we discussed in the last slide. This Pn also includes the noise power generating from the thermal elements, the extrinsic source resistance, the extrinsic gate metal resistance, we include that also in this noise power. This is a gain, this is a gain. See, the noise will depend significantly on the gain, so you cannot compare if your gain is very different in two different device technologies. KT, of course, temperature. So, what is this figure is doing is that they are plotting the noise figure on the y axis, this quantity. However, on the x axis they are plotting the gain. Of course, with higher gain the noise figure will come down, which is good, you know that, right. With higher gain the noise figure will come down, but these different curves 1, 2, 3, 4, this power by KT ratio is held constant for a particular curve. So, what they are doing is that let's keep the noise power divided by kT as your parameter. So, this ratio could be 1, 2, 3, 4, and you can see that as the ratio is increasing from 1 to 2 to 3 to 4, the curve is shifting upwards. That means the noise power is increasing, which is not a good thing, which means the noise figure is increasing. The noise figure is increasing if the ratio, this P by kT or noise power is increasing, which is not a good thing. Of course, we know that. However, what is important here is that this arrow A, it represents that the power Pn is proportional to gain, which means if the power is proportional to the gain, that means this ratio is constant, then F will be constant. Makes sense, it is common sense. Arrow B says that for a given Pn by kT, for a given Pn by ratio, or if you keep this, you can say Pn is constant, kT temperature is constant. So, Pn is constant, suppose. It means with the gain, if the gain comes down this way, the noise figure goes up this way, which also makes sense, but this means that your power is constant along this curve. And C, this is basically if you reduce the gate length or increase the channel material to increase the velocity, then with reducing LG or IDS, you are going to get better or lower noise figure. So, this is what it means. Why am I discussing all this? Because I want to compare an L-gas Hemt, low noise Hemt, with an gallium arsenide low noise MESFET and see in this chart how do they perform. However, comparing two different technologies is very difficult. So, what people have done is that in this chart they are comparing three devices. One is in L-gas Hemt with 0.25 micron gate length, another is L-gas Hemt with 0.5 micron gate length. Okay. Now, if the gate length changes, the gate resistance also will change, which is not a good thing. That is why in this particular study the authors have maintain the same gate resistance by using a mushroom gate or whatever is needed, so that the gate resistance is the same, although the gate length is different. You can use mushroom gate. Okay. They also have maintained the same source resistance by device engineering. They have maintained the same source resistance, same gate resistance, so that the effect is identical. However, they have taken three devices. One is a Hemt with 250 nanometer gate, one is a Hemt with 500 nanometer gate, one is a MESFET with 500 nanometer gate, 0.5 micron. So, what are the conclusions that they are drawing? Very interesting. You can see that the bottom circles are 250 nanometer Hemt, which is the lowest noise figure in general. These black circles here are 500 micron, 500 nanometer gate Hemt. So, you can see if you compare this, which is your 0.5 micron gate length Hemt, this is your 0.25 micron gate length Hemt, you immediately see that the noise figure reduces, or which means it becomes better when you go to shorter gate length 0.5 to 0.25. It is very clear. You can also see that with higher frequency, this is at 12 gigahertz, this is at 20 gigahertz, this is 30 gigahertz, with higher frequency the noise figure becomes worse, or it becomes higher. Why? Because at higher frequency your gain reduces, your gain goes as 1 by frequency. So, if you are higher frequency, your gain reduces, that is why your noise figure also reduces. Okay. And the third thing is the MESFET. The MESFET is this and this. You can see the MESFET noise figure is the worst. Okay, at 0.5 micron, with I am comparing 0.5 micron MESFET with 0.5 micron Hemt, keeping everything same. The Hemt has a better noise figure than the MESFET because the velocity of electron is better. You have a 2D electron gas, screening is better, mobility is better. Okay, so GM is better. You have much better transconductance for Hemt than for MESFET. The channel velocity in a 2D electron gas is also higher than in a 3D, in a bulk kind of a MESFET. Okay, but it also means that if you are looking at just a single curve, say MESFET or a Hemt 0.5 micron, you can see that this is a 12 gigahertz, 20 gigahertz, 30 gigahertz, they all go along a constant line here. If they go along a constant line here, it means that Pn by kT ratio is constant, which means the power, the Pn is fairly independent of frequency, because at a constant power only you are travelling across this curve, correct? At a constant power you are able to travel along the curve. So, what it means is that as long as you are going along this, it means that your power is constant, which means the power density does not, the noise power density does not depend on the frequency, but the gain depends, and that is why Pn, if you remember, Ga by kT. So, this does not depend on frequency, that is why they are going on the constant curve, but this depends on frequency as 1 by f, and that is why the noise figure is increasing with higher frequency, they are going along the constant noise power. So, the noise power is independent of frequency. It also depends on the gate length. I already showed you that. It also depends on the velocity, which also we discussed. So, essentially a Hempt gives superior performance on noise compared to MESFET because of higher electron mobility, better transconductance, higher velocity, okay, a better channel control. Essentially you have higher gain, okay, for the same dimension of device, and that is why it is better. And for a given material system, if you go to a shorter gate length, you get better noise performance. We will see later that if you go to a different material where the velocity is higher, then the noise figure can improve even more. Okay. So, with that we come to a conclusion of this lecture 24, which also brings us to a conclusion of the discussion on L-gas gas Hempt. Okay. We discussed about a little bit about noise performance, we discussed about power performance in terms of the critical process parameters, or I will say the critical device parameter, contact resistance, breakdown, gate leakage, transconductance, etc. So, we know what Hempt is, and how they are operated or how they work, but there are still so many things about Hempts. So, starting next week, lecture 25, we are going to talk about pseudomorphic Hempt, indium phosphide Hempt, metamorphic Hempt. We will see those are the variations or different flavors of L-gas gas Hempts, but which offers substantial performance improvement for millimeter wave power and noise. Okay. So, we will meet you here in the next week. Until then, thank you for your time.